Fitting a regression model requires making several important assumptions about the error terms in the model. First, to estimate the regression coefficients, we assume that the errors are random, uncorrelated, have a mean of 0, and have a constant variance across all observations. These assumptions ensure that the least squares estimates behave well and are unbiased. Another key assumption is that the form of the model is correct. In simple linear regression, this means assuming that the relationship between the predictor and the response is truly linear. If the true relationship is nonlinear or missing important terms, the model may not adequately describe the data. To assess whether these assumptions are reasonable, we examine the residuals. A residual is defined as the difference between an observed response value and its fitted value from the regression model. In other words, residuals represent the portion of the data that the model does not explain. Here we can see 4 common residual patterns and what each one tells us about the adequacy of a regression model. In all panels, the vertical axis shows the residuals, denoted by epsilon(i), and the horizontal line at 0 represents no error. Panel, a random scatter around 0. The residuals are randomly scattered around 0 with roughly constant spread and no visible pattern. It means linearity assumption looks reasonable. Constant variance, homoscedasticity, is satisfied. And errors appear independent. This is what we want to see when a regression model fits the data well. Panel, the increasing or decreasing spread, non-constant variance. The spread of residuals increases as we move across the horizontal axis, forming a funnel-like shape. This means variance of errors is not constant. The assumption of homoscedasticity is violated, and possible remedies include transforming the response variable or using weighted least squares. Panel, see clustering or structure, correlation or missing variables. Residuals show structure or grouping rather than randomness. This means errors may be correlated. Important predictors may be missing, and there may be time order effects or omitted variables. Panel, D-curved pattern, model misspecification. The residuals show a systematic curved pattern rather than random scatter. This means the linear model is not capturing the true relationship. A nonlinear term or higher order model may be needed. And this suggests the order of the model is incorrect. When we move beyond parameter estimation to hypothesis testing and confidence interval construction, we make an additional assumption. The errors are normally distributed. This normality assumption allows us to use the t-distribution and the f-distribution to make valid statistical inferences. As an approximate check for normality, we often construct a normal probability plot, also known as a Q-plot, of the residuals. If the residuals follow a normal distribution, the points in this plot should fall approximately along a straight line. Significant departures from this pattern may indicate violations of the normality assumption. A Q-plot works by comparing the quantiles of the observed data to the quantiles of a theoretical distribution, most commonly the normal distribution. Each point on the plot represents a pair of corresponding quantiles, one from the data and one from the theoretical distribution. When the data closely follow the theoretical distribution, the points align roughly along a straight line, indicating that the distributional assumption is reasonable. However, we should be cautious when interpreting systematic departures from a straight line. Different patterns suggest different issues. Curvature indicates skewness. S-shaped patterns suggest heavy or light tails. Large deviations at the ends point to outliers or non-normal tails. In regression analysis, Q-plots are most commonly used to assess whether the residuals are approximately normally distributed, which is essential for the validity of hypothesis tests and confidence intervals. In this particular plot, the points lie approximately along a straight line, with only minor deviations at the tails. This pattern suggests that the residuals are reasonably close to normally distributed. Small departures at the extremes are common in real data and do not appear severe enough to cause concern. R-squared, also known as the coefficient of determination, measures the proportion of the total variability in the response variable that is explained by the regression model. An R-squared value ranges between 0 and 1, where 0 indicates that the model explains none of the variation in the response, and 1 indicates that the model explains all of the variation. In simple linear regression, R squared is directly related to the ANOVA decomposition. Specifically, it is defined as the ratio of the regression sum of squares to the total sum of squares, representing the fraction of total variation explained by the fitted regression line. While R squared is informative in simple linear regression, it has an important limitation when moving beyond this setting. It never decreases when additional predictors are added to the model, even if those predictors do not meaningfully improve the model. To address this issue, adjusted R squared modifies R squared by accounting for both the number of predictors in the model and the sample size. In doing so, it penalizes the inclusion of unnecessary variables and provides a more balanced measure of model performance. By default, Python regression output reports both R squared and adjusted R squared for fitted regression models. In addition, R squared can also be computed manually using the ANOVA quantities, as shown here. Instead of visually confirming the adequacy of the fitted models, we can also rely on hypothesis tests and statistics. So far, we have been using hypothesis tests to hypothesize over the valley of population parameters, and now we see that we can use hypothesis testing to confirm the distribution of data. For example, both Omnibus and Jarque-Bera tests can assess whether residuals display normally distributed behaviors. Both tests assess normality of residuals using skewness and kurtosis. Jarque-Bera is a specific, well-known test, while Omnibus is a broader joint test. When both agree, confidence in the normality assumption increases. Note the main weakness of both these tests are that we need to fail this test to report residuals are normally distributed. Skewness measures the asymmetry of the residual distribution, where a value close to 0 indicates symmetry, which is what we look for. Kurtosis measures the tail heaviness of the residual distribution. For normal distribution reference, kurtosis score should be around 3. Having lower numbers indicates lighter tails and larger numbers indicate heavier tails. Durbin-Watson statistic measures the autocorrelation between residuals. We want to see a Durbin-Watson statistic of 2 which signals no autocorrelation to confirm the independence assumption. Condition number measures numerical stability and multicollinearity, and we target a score less than 30 for this statistic. The blue dots represent the observed data points used to fit the regression model. The blue straight line is the fitted linear regression line, which serves as a model-based approximation of the relationship between the predictor x and the response y. The red curved line represents the true function, the underlying relationship that generates the data, which is unknown and may not have a simple closed-form expression. Within the range of the observed data, shown by the green shaded region, the fitted linear regression line provides a reasonable approximation of the true relationship. In this region, the model is supported by data, and its predictions are generally reliable. However, the figure also highlights what happens when we consider a new input value of x that lies outside the range of the observed data, shown by the red shaded region. In this region, we have no data to inform us about how the true relationship behaves. Even though the fitted line performs well within the observed data range, there is no guarantee that it will continue to perform well beyond that range. If the true relationship is nonlinear, extrapolating with a linear model can lead to large prediction errors. This illustrates a key limitation of regression models. Extrapolation is inherently risky and unreliable. A model that fits the data extremely well can still produce poor predictions outside the range of the data used to build it. That being said, we can use the fitted model to interpolate. Interpolation refers to making predictions within the range of the observed data, where the predictor values fall between the minimum and maximum values used to fit the model. These predictions are generally more reliable because they're supported by nearby data points. In interpolation, the model is being used in a region where it has already learned the relationship from the data. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.